Maybe now's the time to begin. So let me welcome you all to the first of this fall series in the Princeton-Bucharest Seminar in Early Modern Philosophy. It's nice to see so many familiar faces back. And today's program is going to be about Leibniz. There are going to be two papers. The first by Filippo Constantini from the University Ca' Foscari of Venice and McMaster University, speaking on Leibniz mereological characterization of quantity. And the second speaker is going to be Jeffrey Elouani from McMaster University and University of Paris, who's going to be talking about estimating quantity, the procedure for knowing how much of a thing there is. The two papers are going to be given in succession without questions in between. But at the end of both papers, there'll be a joint discussion session. Okay, Filippo?
Okay, thanks very much. I'll share my screen. Can you see it?
Yes.
Okay. Just need to, sorry. Okay, so before starting, we would like to say a couple of things. So first of all, we wanted to thank the organizer, not only for having us today, but also for the passion that you had since this panel was originally scheduled for the spring session and we had to cancel it. So we really appreciated the fact that you allowed us to postpone the panel. And the second thing is that the two talks that we are going to present today, they are really two different parts of the same work that Jeffrey and I are doing together. So I'm going to cover some more preliminary issues about this notion of about Leibniz's way of estimating quantities, while Jeffrey is going to give a more precise mathematical description of this estimation procedure. Okay, so I'd like to start. Well, I just need to close here. Sorry, just. Okay. Okay, so I'd like to start by pointing out that we find in Leibniz at least two different conceptions of number. So one conception can be found in passages such as this one from the 80s. Identical things are those that can be substituted one another salva veritate. If A is D and B is D, and C is D, and A, B, and C are the same, then D will be one, unum. If A and B and C are different, each one from the others, they are a plurality from which we have numbers. Now, in these passages, in this kind of passages, what Leibniz is trying to do is to use logical relations such as identity and diversity to introduce numbers. So we follow David Rabouin in calling this conception the logical conception of number. And notice that this is a bottom-up approach to the concept of number, because first of all, what Leibniz does is to define essentially the number one or the unit by means of the identity relation. And once he has introduced this notion, he exploits the the diversity relation to introduce any kind of finite pluralities, and so any positive integers. So essentially, before he defined one, and then he goes on defining all other numbers. And for this reason, we call a bottom-up approach. And this approach can be found in many other passages where, for example, Leibniz says that we can, if we start with the abstract unit, and by adding the abstract unit to itself, we can generate all the finite integers. Now, this is not the conception of number that we are interested in our talks. We are rather interested in a different conception, which we call the estimation conception of number. And estimation because here numbers are like the result of the estimation procedure that Leibniz develops to compare continuous quantities. And here the important point is that this is a top-down approach, because basically what is going on is that Leibniz starts with continuous magnitudes. He compared them, he tried to estimate their ratio, and this estimation is nothing than the division of a continuous magnitude into parts. So we start with a whole magnitude and we break it down into parts. So for this reason, we call a top-down approach. And as a result of this estimation procedure, we get the notion of number. So this estimation conception of number is the one that is captured by what is maybe the most famous characterization of number that we find in Leibniz. So for example, when Leibniz says number is homogeneous to the abstract unit, or here is another passage, number is homogeneous to the abstract unit, and so it can be compared with the unit, and it is said to be added to it and subtracted from it. Now, the main claim that I want to make in my talk is that the estimation procedure that Leibniz develops can vindicate both this characterization of number, so the idea that numbers are homogeneous to the abstract unit, but also another famous claim that Leibniz made, especially in the young years, that natural numbers, that is positive integers, are collections or wholes of abstract unities. And what I want to show is that that these two claims can be vindicated, and so should be understood in terms of this estimation comparison, this estimation procedure. So our idea is that this estimation procedure is really has really a central stage in Leibniz philosophy of mathematics. And in terms of this procedure, we should assess a number of different problems, such as the question of infinite numbers, infinitesimals, the relation between potential and actual infinite in mathematics, and so on. Okay, so what I'm going to do in this talk is I will start with the distinction between fine and imperfect estimation. And we will see that this distinction relies on the homogeneity condition. I will then speak about the relation between estimation and mereology, so the theory of the parthood relation. And here the main point to bring home is the fact that we can apply the estimation procedure that Leibniz had in mind to magnitudes, just because magnitudes have a mereological structure, so they can be decomposed into parts. I will then explain in which sense these two claims should be understood in terms of this estimation procedure. And finally, we say a few words on the role of numbers in essentially Leibniz theory of measurement. So about the distinction between fine and imperfect estimation. So a fine estimation is an estimation between homogeneous magnitudes, homogeneous objects, And here the key aspect is that there is always a ratio between homogeneous magnitudes. So for example, we have passages like this one where Leibniz says that we can find ratio between homogeneous and homogeneous objects, and this is just by definition of homogeneity. Or here is another passage. Among all the relations, the simplest is that which is called ratio or proportion, namely a relation between two homogeneous quantities, which originates only from them without assuming a third quantity. And so in this passage, Leibniz is saying that ratio or proportion is the simplest relation between magnitudes, because we don't need to consider a third external object to determine the ratio between two magnitudes. But he also stresses that we have a ratio between homogeneous quantities. So homogeneity, when A and B are homogeneous, we know that there is always a ratio between them. Now, the imperfect estimation is an estimation between object magnitudes which are not homogeneous. And one famous example is the example of the angle of contact, which is not homogeneous to the rectangle angle in which it is contained. Another example would be the relation between a point and a line in which the point is contained. And in this case, Leibniz says that in some cases, here we don't have a ratio. So there's no ratio between a point and a line in which it is contained, but still it is possible to determine, well, in some cases at least, whether given two objects, for example, a point and a line, which is the bigger and which is the smallest. So for example, we can say that the point, there is a sense in which the point is smaller than the line, even though they are not homogeneous. Now, the point of introducing this distinction is to say that Leibniz estimation procedure is a case of a fine estimation. So it relies on homogeneity. And so from now on, when I'm talking about estimation, I've got in mind the case of fine estimation and not imperfect estimation. Now, since the case of fine estimation relies on homogeneity, we should say something about this really important notion. So essentially, homogeneity capture a condition for comparability, and in many passages, Leibniz says that it is a necessary but also a sufficient condition for comparability. So for example, if of two things, one is bigger, smaller, or equal to the other, then they are homogeneous. And the basic idea is that homogeneity should express the Archimedean property. Now, contemporary characterization of the Archimedean property, a possible characterization is this one. So if you consider an ordered field, for example, the field of real numbers, and you pick up two arbitrary positive magnitudes in this field, so two positive real numbers, well, then there is always a strictly positive integer n, such that if I multiply one of these arbitrary magnitude that I've considered n times, I can get something bigger than the other magnitude. So the idea is really that when the Archimedean property holds, I can always compare objects that satisfy this property, in the sense that if we suppose that x is smaller than y, well, I can multiply x a finite number of time to get something bigger than y. Now, it is interesting to notice that this is not how Leibniz usually characterizes the homogeneity condition. He usually gave a different definition. And the reason seems to be that in this characterization of the Archimedean property, where we are using the notion of integer, so we must already have the notion of positive integer, natural number. While what Leibniz is trying to do is, in a way, taking an opposite direction. So he defines homogeneity without appealing to the notion of positive integer. Homogeneity is then a necessary condition for the estimation procedure. And numbers in general, so positive real numbers, are just the result of the estimation procedure. So the reason why it doesn't give this definition of homogeneity is because it would be a circular definition if we take into account what it's trying to do. So my favorite Leibnizian definition of homogeneity is the following. Two entities are homogeneous to which two other entities can be assigned which are equal to them and similar to each other. Now, this is taken from Initierum Mathematicarum Metaphysica. And essentially, to understand what is going on here, that's my suggestion, we should look at this picture. So the picture represents a case in which X and Y are homogeneous objects, but they are not similar. They are not similar because similar objects share all their qualitative properties, while in this case, X and Y, X is a circle, Y is a triangle, so there are many properties that one object has and the other lacks. However, X and Y are correlated with two other objects, V and W, in such a way that X and V are equal, and equality is a quantitative identity. So this means that from a quantitative point of view, X is identical to V. In this two-dimensional case, what we are saying is that they have the same area. And the same for W and Y, which are equal. V and W are similar. So they share all their intrinsic properties. In this case, we have like two hexagons. And the idea is that when we have two similar objects, we can always compare them with respect to their magnitude, so with respect to their quantity. And this just follows from one of the standard characterization of similarity that Leibniz presents. Sometimes Leibniz says that if A and B are similar, well, then to distinguish them, we must look at their difference in quantity, and difference in magnitude. So the idea is that V and W are similar, so we can compare them. And for example, in this case, we can establish that the area of V is less than the area of W. So V is less than W. And then we can exploit the equality relations. So we can exploit the fact that V is equal to X to substitute V with X. And we can exploit the fact that V is equal to Y to substitute W is equal to Y to substitute W with Y. And when we perform this double substitution from V is less than W, we get that X is less than Y. So the idea behind the definition of homogeneity is that we can take a judgment about similar objects, so a judgment in which we are establishing a quantitative comparison between similar objects, and we can extend these quantitative comparisons to objects such as X and Y, which are not strictly speaking similar, but are homogeneous. So they are related to similar objects via some transformation that preserves equality. So homogeneity allows us to extend the class of objects that we can compare. And okay, at this point, I think I should say two more things about homogeneity. So the first thing is that if A and B are homogeneous, then they must have the same number of dimensions. So for example, in the picture, I consider like two dimensions object, but I could have considered any number of dimensions. So for example, two lines are homogeneous to each other, two-dimensional objects, so like two-dimensional figures are homogeneous to each other, but a point is never homogeneous to the line because a point has no dimension, the line has one dimension. And the second thing to notice is that if I consider a finite magnitude, so for example, I consider a finite line and I consider an infinite line, well, they are not homogeneous. I mean, to see why, if you think about the Archimedean property, it can never hold, the Archimedean property can never hold between a finite and an infinite magnitude, but more generally for Leibniz, an infinite magnitude is something that, strictly speaking, implies a contradiction. So actually, there cannot be really infinite magnitudes. Okay, so that was like the part on the notion of homogeneity, and homogeneity is an accessory condition for the fine estimation, and so it's an accessory condition for the estimation procedure that Leibniz develops. Okay, so at this point, we can have a look at this estimation procedure. And here I've got a passage from the 80s, where Leibniz summarized in few lines this procedure. And essentially what is going on here is that this procedure is nothing else than the Euclidean algorithm to estimate or to determine the greatest common divisors between integers. Is simply the fact that what Leibniz is doing is to generalize this algorithm and applying it to any homogeneous quantities. So here he says, to compare two quantities in themselves without assuming an extrinsic measure means to subtract the smaller from the bigger as much as possible, and the remainder from the smaller also as much as possible, and the second remainder from the first, and so on, until there is no remainder left, or it appears that the future progression of quotients or the number of subtractions go on into infinity. I call this the series of quotients of comparison. So the first things to notice is that this passage and also other passages seems to suggest that Leibniz thinks that we can apply this estimation procedure every time we have homogeneous magnitudes. Now, this is not really the case, and there are limitations to the application of this procedure, especially when we are dealing with intensive magnitudes. But this is a topic that Jeffrey is going to deal with more extensively. So for the time being, we can just think that when Leibniz is thinking of comparing magnitudes, is thinking of this estimation procedure. The other things to notice is that the procedure is based on the notion of subtraction and the notion of remainder. Now, subtraction here is not arithmetical subtraction, but rather it is mereological subtraction, because we are working with magnitudes and we are subtracting parts of one magnitude from itself, essentially. And now the question is, what allows Leibniz to apply mereology when dealing with magnitudes? And essentially the answer is given by this passage. So in more than one passage, Leibniz made this kind of claim. We can define the quantity of a thing as the property of the whole insofar as it has all its parts. Actually, I think that there is something more. So we can argue that in Leibniz we have not only the fact that if x is a quantity, then x is a whole with parts, but we have also the converse. So we have that x is a quantity if and only if x is a whole with parts. And essentially this allows Leibniz to apply mereological principle in the estimation of quantities. So this idea that when we have a quantity, we have a whole with parts. Okay, so let's try to understand better how this estimation procedure works. So consider two magnitudes, in this case, two lines, A and B. And the idea is that we take A as our measure, for example, and we start subtracting from B, which is the biggest line, a part of B, A prime, which is congruent to A. Congruent means that if I superimpose A and A prime, I cannot discern them anymore. So they are also equal. They have the same quantity, essentially. So I subtract from B A prime. And once I've done this, well, I consider B minus A prime, and I subtract from B minus A prime another part, A second, which is congruent to A. And then I go on in this way until it is no longer possible to subtract parts congruent to A. And if at a certain point I obtain a remainder in B, so a part of B, which is smaller than A, well, I start subtracting from A parts of A congruent to the remainder. And again, I go on, and the procedure can stop, but if the ratio between A and B is commensurable, it won't stop. So essentially, the estimation procedure just consists in the merological subtraction from one magnitude, so from the biggest one, of a part congruent to the other magnitude. So the measure is simply the one of the two magnitudes. So I can consider as a measure any magnitude I want. Okay, so it's really this merological subtraction. And indeed, we have this passage. The method of comparison consists essentially in the continuous division or subtraction of the possible remainders. Essentially, division is nothing else than the repetition of subtraction, a repeated subtraction. So here, the really important concept is the concept of part, is the part-to relation. And Leibniz defines part in the following way: X is a part of Y, means that X is in Y, so X is containing Y. The relation is the in esse relation. And X and Y are homogeneous. So since they are homogeneous, we know that essentially the part is always comparable with the whole. So there is a ratio between the part and the whole. And another point to keep in mind, very important, is that when I subtract, for example, A prime from B, and so I get B minus A prime, I can call this C, well, then C and A prime are disjoint. So, which means that they have no part in common. Now, this is a very subtle point, because essentially this disjointness just follows from the definition of merological subtraction that we find, for example, in the papers on real addition. But it's a subtle point because this disjointness is defined with regard to the notion of partude. So it is still compatible that, for example, we have a point in common between B minus A prime and A prime, because a point is not homogeneous to the lines, and so it's not a part of A prime or B minus A prime. And this is really important because if we look at Leibniz's definition of continuity, so here we are working with continuous magnitudes. Well, one of the property that defines continuity is the fact that if we essentially cut a continuous magnitude, we are cutting it in a point, and the cut will divide the magnitude into two parts, which, according to this definition of continuity, that these two parts must have the point in which we have cut the magnitude in common. So the point is shared by the two parts. So essentially, the idea is that when I cut B into C and A prime, while the point where I cut is in common is both in B minus A prime and in A prime. But still they are disjoint with regard to the notion, to the partude relation, because the point is not a part of the line. Okay, so this is a subtle point, but it's very interesting. I really like how Leibniz is very careful with all of this. All right, so now, I mean, we have seen the estimation procedure, and essentially, basically, the idea is that when we should estimate, we take a magnitude and we divide that magnitude into parts congruent to another magnitude. So it's like a division procedure. But there is also another way of looking at this estimation procedure, which is essentially the following. Again, we consider A and B. And the idea is that we can estimate the ratio by repeating, in this case, like A. So we take A as a measure and we repeat our measure. So basically, the idea is that by repeating the measure A plus A plus A, we should be able to estimate the ratio. So at a certain point, we may cover all B, or we may not cover B, and again, we find a remainder. And if we find a remainder, then we take the remainder, we repeat the remainder to cover A. And again, here, I mean, the procedure can stop or cannot stop. So essentially, we should go on until it's no longer possible to apply the algorithm. Now, here we have a problem, though. And the problem is the idempotence law for mereological addition. This is a law that is explicitly stated in Leibniz real addition papers. And essentially is the idea that if I take an object and I sum to itself, to the object itself. So if I take A and I take A plus A, I won't get anything new. And this is a very common law to have in mereology, because mereology should apply to any kind of entities. So if I consider, I don't know, this pencil, and if I add to itself, to the pencil itself, I won't get anything new. But clearly, since the idempotence law, it seems that I cannot think of this estimation procedure as the repetition of a measure. Because if I repeat A plus A plus A, no matter how many times I repeat A, at the end, I will just get A. So to overcome this problem, essentially Leibniz introduced this notion of partes extra partes, which can be seen as like a restriction of mereology to disjoint objects, so to objects that have nothing in common, so no part in common. And basically the idea is that when I repeat the measure, A plus A plus A and so on, what I'm really doing is considering A, and then when I repeat A, I'm actually considering a different object, which is external to A, so it's a part extra partes, so it's external to A, but it is congruent to A. And so it's like A prime, where A prime and A are congruent, but they are different objects. So they don't have any part in common. And then when I again repeat A, I'm really considering a new object external to the two preceding objects, which is, however, congruent to our measure. So what really matters is that I'm considering parts or objects which are disjoint and congruent with each other. And in this way, I can think of the estimation procedure as the repetition of the same measure. Okay, so this is essentially another way of looking at the estimation procedure, and it's very important because when we cannot apply this idea of partes extra partes, well, then we cannot apply this estimation procedure. And indeed, it is a problem in some cases with regard to intensive magnitudes that we can apply this idea of partes extra partes. All right, so until now, I spoke of homogeneity. I spoke about the relation between mereology and estimation. So mereology is another necessary condition for the estimation procedure. And now I come to the two main claims of my talk. So again, so here I'm dealing with the claim that natural numbers are wholes of units. Again, consider A and B and suppose that the ratio between B and A is 4:1. Which means that when I divided B, I can divide B in 4 parts congruent to A. Now, clearly, the same ratio can be found in many other different cases, in infinitely many other cases. So, for example, if you take these two squares, they have, by supposition, the same ratio, 4:1. This shows that the ratio is a more abstract notion than the notion of magnitude. And if we want to introduce ratio in a rigorous way, we should introduce it as an equivalence class of magnitudes. But the point is that when we think of this estimation procedure as a division procedure, well, and so we divided the line B thanks to A, and we divide the green square thanks to the blue square, well, we get essentially in both cases a collection of parts congruent to our measure. And if we take the measure as like the unit measure, so the abstract unit, what we get is essentially a collection of parts congruent to the abstract unit. So if we don't care that in one case we have lines and in the other case we have squares, essentially we get the notion of positive integers as a collection or as a whole of abstract units, because we have these parts congruent to the abstract units. We have a finitely amount of parts congruent to the abstract units. So this claim that natural numbers are wholes of unit should be understood or can be vindicated by looking at this estimation procedure. It's just a special case of this estimation procedure. It's the case in which there is no remainder when we compare the two magnitudes. A similar story can be told for the other characterization of numbers, so number as what are homogeneous to the abstract unit. Now, numbers in general, and here I've got in mind positive real numbers, are the result of this estimation procedure. And so if we have no remainder there, we get a positive integers. If we have some remainder, then we go on applying the estimation. If the estimation stops, we get a rational number. If the estimation won't stop, we get an irrational number. So when Leibniz sometimes writes stuff like this, the quantity of something is expressed by the number of the non-communicating, so the disjoint parts of the same measure congruent to the unit, is not defining quantity in terms of number, but it is rather describing this the result of this estimation procedure. In this view, so numbers, what they do is to express the ratio between homogeneous magnitude. And if we take one of these magnitudes as the abstract unit, then the resulting number will express the ratio between a magnitude with the abstract unit. And for this reason, numbers are homogeneous to the abstract unit. So they are comparable with the abstract unit. And exactly because if we take two magnitudes and one of them we consider the abstract unit, then we apply the algorithm to determine the ratio. Well, the number that we get will express the relation between the ratio between the abstract unit and the magnitude and the other magnitude. So in a way, numbers are homogeneous to the abstract units. Again, it's just a result of this estimation procedure. Okay, so this essentially covers like the main claim I wanted to make, that these very important claims that Leibniz made about numbers. So integers are as wholes of units and numbers as what is homogeneous to the abstract units should be understood in terms of this estimation procedure. I will now briefly conclude with just a very small epistemological reflection. So in this setting, essentially, we have that this estimation procedure is really at the center of the stage. And what about numbers? Well, for example, what about positive integers? Well, they are not basic entities, but this is an epistemological claim. It's not a metaphysical claim. So with this, I just means that essentially positive integers, but also all positive real numbers, they are only a result of this estimation procedure. So what is more basic from an epistemological point of view are the continuous magnitudes. And indeed, Leibniz stresses a lot the fact that when we are dealing with ideal entities, magnitudes are given as a whole, and the whole here is prior to the part. So for example, this is a very famous passage that exactly expresses this view. In the ideal or the continuum, the whole is prior to the part, as the arithmetical unit is prior to the fractions which divide it, and which can be assigned arbitrarily. Its parts are merely potential. In the real, however, the simple is prior to the aggregates, parts are actual and are prior to the whole. So this estimation procedure, which is essentially Leibniz theory of measurement, should be understood within a broad, like Aristotelian epistemology, where we should start from what is prior for us. And what is prior for us is not what is prior in nature. what is prior for us, what is given in perception, essentially is continuous magnitude. And by breaking down continuous magnitudes, we can get to the notion of number. And once we have done that, we can move to the metaphysical aspect of the project, and we can try to account for example, extension and so on in terms of discrete entities. But yeah, I mean, my suggestion would be to look at this estimation procedure as a procedure that lives within this broadly Aristotelian epistemology. And with this, I conclude. So thanks a lot for your attention.
Thank you. Thank you very much, Filippo. We're going to move directly to the second talk. Jeffrey Elawani, McMaster University and University of Paris, Estimating Quantity, the Procedure for Knowing How Much of a Thing There Is. Jeffrey?
Good. Thank you, Professor Garber. So let me just share my screen and get my timers ready too. Hold on, so I don't lose track of time. Okay, good. Well, first, I want to say I'm very honored to be here, and I want to reiterate that we're very grateful towards the organizers for allowing us to present this fall instead of last spring. I'm looking forward to air your insights and feedbacks on what we have to present today on this material. So as Filippo mentioned, my own talk will focus on the preferred or privileged method for fine estimation in Leibniz on a generalization of Euclid's algorithm, which algorithm is designed to find the greatest common measure between two line segments representing numbers. In the talk, what I want to do, I want to scrutinize this preferred method, and I want to lay out how it allows for precise and exact determination of magnitudes of different kinds under three conditions. So what I hope ultimately is that you will find that there are interesting consequences which follow from the scrutiny of this privileged method, both for Leibniz's philosophy of mathematics and for his physics too. So let us get going. So the plan for today is as follows. First, I will just do a very quick recap and say one or two things about fine estimation in general. Then I'll try to motivate why it is interesting, why it is instructive and also legitimate to look at estimation and at the exact knowledge of magnitudes in Leibniz from the point of view of this preferred method for estimation, which I will call the mathematician's estimation. Then I will present Euclid's algorithm very quickly, so just everybody is on the same level. Here, my aim is not for historical accuracy. What I want to do is just convey enough information so that the method for estimation here is made intelligible to everyone. After that, I will move towards the mathematician estimation as it applied to magnitudes of different kind. What I want to do here is using the example of line segment as a guide. So line segment are the objects to which Euclid's algorithm is designed to apply. So using them as an example, as a guide, I want to see how the mathematician's estimation allows for an exact determination of quantity in general. To do this, I'll focus on three conditions present in Leibniz. These are laid down here. And it is under these conditions that the procedure is made general and that we can have a exact estimation of magnitudes and things of different kinds. And to conclude, I'll just lay down the mathematician's estimation more formally and try to lay it down in 4 or 5 sentences so you can see how it applies for magnitudes in general in a condensed picture. So let us get going. First, fine estimation. So what's important to keep in mind here is that fine estimation of the quantities in things is a comparative procedure. What is specific about it is that it determines exactly the ratio of two things, or it determines exactly by how much something is bigger than one other. So to put things in a more formal way, I offer the following definition of estimation. So here, when I speak of estimation, I always mean fine estimation. So more formally, the method of estimation of the magnitudes A in a thing XA associates a number R to the quantity A in relation to an actually given measure or unit M, or equivalently, it yields a ratio of A to M. So these are really just two ways to look at estimation. They're equivalent. You can either look at it as the ratio of the estimated thing to the measure that you fixed, or you can look at it as the ascribing of a number R to a quantity A in relation to a measure that you fixed before. Here, I won't insist on it in the talk, in the rest of the talk, but it's important to say that for Leibniz, the measure must be actually given or presented. It cannot be conceptually grasped. So it's often the case in Leibniz that the number R that I mentioned is expressed in terms of the number of disjoint parts of the thing XA. These disjoint parts must be congruent to either the measure M that is fixed or to a refinement of M. So what is a refinement of M? Basically, here, it's something that's very simple. If you have a scale and you try to measure something against the scale and it falls between 2 points of your scale, what you can do is you can divide the scale further. So for example, you can bisect it or use another method of division. And then what you have is either the thing will fall on this new point or it will fall between in either one of the interval generated by this new point. And then what you have is you have a finer approximation of the magnitude of the thing. So it's important to say, as Filippo already mentioned, that this procedure for estimation is often put in terms of the repetition of a magnitude of a measure by Leibniz. So for example, in this text, which bears on estimation of things in general, Leibniz writes, every estimation by means of a definition of magnitude comes down to the repetition of a certain measure expressed by numbers. So this may seem at first, and it may suggest that this phrasing in terms of repetition of a certain measure is kind of restrictive, in the sense that it's saying that a thing estimated by a measure in this sense must be something that stands to the measure as an integer stands to a unit. Well, this is not the case, obviously, because as Filippo already pointed out, Leibniz wants this estimation to work for any kind of number, so it has to apply to ratios which are irrational. So this is one of the upside of looking at things from the point of view of the mathematician's estimation that is based on Euclid's algorithm. It is that it helps us to see why the definition in terms of the repetition of a measure is not restrictive. Why is that? Well, if you have a ratio between two things which stand to each other, not as an integer to a unit, but as a fraction of two integer, or as something that is irrational, then what you can do is just you apply your Euclidean algorithm, or the division in turn that Filippo mentioned. What it yields is a sequence of quotients. And what are those quotients? Well, they're just repetition of different measures. So basically, everything always boils down to repetition of measure. And so framing things in terms of repetition of measure is not restrictive in any way. And we see why it is natural to speak in such way. And it's not then strange for us now. One other reason why it is legitimate to look and instructive to look at this mathematician's estimation is that it figures prominently in Leibniz. So to the point where Leibniz sometimes presented as the method for comparing quantities, or as the way in two quantities whatsoever compare, the way in which A compares with a unit M. And last, also, there is the fact that other methods of estimation that are based on the repetition of a measure do not seem to differ substantially from this one. That is, if you look, for example, at this passage from the specimen Luciferae, what Leibniz says there is that in case where you measure things using another method than that of the mathematician estimation, then that based on Euclid's algorithm, what you do is you make your refinement according to a geometric progression. So for example, you will do a bisection iteratively, but all the rest is the same. It boils down to the repetition of a measure. So in the case of the mathematician's estimation, how you do the refinement is you use Euclid's algorithm. So these are the reason why it's interesting to look at things from the point of view of this preferred method or particular method of estimation. So let's have a look at Euclid's algorithm. I'll be very quick here. So basically, Euclid's algorithm is based on a procedure called antiphrasis, which is a Greek concept meaning taking away in turn or division or removing parts in turn. So it's very close to what we now call a division with a remainder, with the exception that it applies to any kind of line segments. This means that the procedure of division in turn may not all or may not terminate. So it's possible that you always have a remainder and you must always keep going on. So this is different from what we're taught at school, where at some point the procedure must halt. So antiphrasis is basically the subtraction procedure that Filippo already presented. As I just mentioned, it applied to straight lines in general, so it's not restricted to straight line representing integers, as is the case in high school now. It applies to positive magnitudes only, which is cogent or normal when we deal with measurement. So there is no question of oriented segments here. And last, it's important to say also that this procedure of division was well known among Greek mathematicians at the time of the elements. It was also known to Aristotle, which says that it determines the ratio in case where two magnitudes are incommensurable to each other. He said this in the Topics. And at the time of Leibniz, it is also known to many mathematicians at the time that antiphrasis determines ratios by a sequence of quotients. So what is Euclid's algorithm? Well, it applies antiphrasis or division in turn to two numbers represented as line segments and results in their greatest common measure if there exists a common measure between them. So let's have a look very quickly at one example. So in the rest of the talk, I will always consider magnitudes that are unequal when I consider comparison. This is because in case where you have equality, it's very trivial. So basically then your common measure is either one of the two things that you're working with. And if you want to ascribe a number to either one of them, the number will be one because the measure against which it is measured is just the same thing. So let's consider the case where the segment A is bigger than B. Then what happens? Well, this is the step one. Step two, what we want to do is we want to subtract the smaller from the bigger as many times as possible. So we want to remove B from A as many times as possible. So here we will say that it can be subtracted 3 times from A, for it fits 3 times in it. There are three parts that are congruent to B in A. And suppose that there is also one remaining part, R1, that is left. So this is the picture here that we got. So here you see that you have a quotient as 3 because the quotient will register the number of repetitions of congruent parts. Basically, this is simply division with a remainder where A is equal to 3B plus 1. Since we have the remainder, we have to do the same thing again. So we're back at step 1. We compare the remainder against B. Now, we have that R1 must be smaller than B. Why is that? Because otherwise we would not have respected the instruction of removing B as many times as possible from A. It would have been the case that we could have removed B one more time at least from A. So it must be that R1 is smaller than B. So we're back at step 2 where R1 is B and B is A. Now we want to remove R1 as many times as possible from B. So let's say that it can be subtracted 2 times with a remaining part R2. So basically, again, what we have is division with a remainder where B is equal to 2 times R1 plus R2. Here, the quotient is 2 because we have two repetitions of congruent parts equal to R1 in B. Now, again, we had a remaining part R2, so we want to compare R2 against R1. It's again step 1. For the same reason, again, R2 must be smaller than R1. So what we do, we subtract it as many times as possible. Let's say that R2 fits just exactly 2 times in R1. So what we have here, we have a division without a remainder. That is, R2 is a divisor of R1. We have that R1 is equal to 2 times R2. And so we're brought to our last step. Now that we have reached the last non-null remainder, here R2, we stop. R2 is the greatest common unit or measure for A and B. And we have that if we make the substitution in our sequence of equation, the one that we obtained earlier, we can see that B is to R2 as 5 and A is to R2 as 17. So if we pick R2 as a measure, we have that the number ascribed to A will be 17 and the number ascribed to B will be 5. This is the mathematician estimation of the line segment A and B in terms of R2. Now notice that if we estimate the line segment A in terms of B, we have that the number ascribed to A will be 17 over 5. That is that if we pick a measure M, then the number associated to a magnitude A will be the ratio of A to M. So this is the equivalent point of view that I was talking about. These are the equivalent points of view that I was talking about earlier. So now we see that the mathematician's estimation uses Euclid's algorithm to yield the ratio between the two line segments A and B. Notice that A and B have nothing special. So more generally, the mathematician's estimation uses Euclid's algorithm to characterize the quantity of a line segment X relative to that of a line segment Y by the procedure of antipharesis. Leibniz still likes to put things in terms of seeking a common measure or finding a common measure, even in fact where there are no common measures. That is in fact where the two quantities, that is in case where the two quantities at stakes are incommensurable. Well, why is that? It's because it says that it is as if we can always find some measure that is almost a common measure for both of them. Basically, this seems to be based on the fact that Euclid's algorithm will yield very good rational approximation of an irrational ratio. That is a ratio between two incommensurable magnitudes. So what you can do is you can just apply Euclid's algorithm to this ratio that is rational and very close to your irrational ratio. And this ratio of rational will have a common measure. And this measure is almost the common measure for your ratio of incommensurable. And it is one of the quotient in the sequence of quotient associated to your ratio of incommensurable also. So now I want to turn over to the mathematician's estimation of general. So what I want to do exactly here is I want to build up to this estimation. And I propose to scrutinize how 3 general conditions placed on estimation by Leibniz play a role in the implementation of this particular method to magnitudes in general. So basically, I want to see how under these 3 conditions, we can have an exact measure of, we can have an exact determination of magnitudes in different kinds of things. So the conditions are as follow. We have that the things compared must be homogeneous. So the measure and the thing it serves to estimate must be homogeneous. We have this condition of extensivity. That is that the magnitude in the thing estimated must arise from the numbers of its disjoint parts of different magnitudes. And last, we have this condition that I call the fine estimation condition, and which consists in the fact that there must be a procedure to assess that the comparison we're doing is exact. So let's turn to each of the three conditions. Now, first, the homogeneity condition. So notice that antipharesis supposes that the two numbers represented by the line segment satisfy the Archimedean property, which Filippo already presented. Basically, here in the case of line segments, we have that a line segment A, that for any two line segments A and B, there must exist some n natural such that A is strictly smaller than n times B. So in the way that I presented things, I think that it is kind of explicit. It is kind of plain that this property must hold. Why is that? Because I had this instruction of subtracting as many times as possible. So if you deal with two things that are not comparable in the sense of Archimedes, then what happens? Well, the instruction is just not valid because there will not be any n such that the smaller taken n times is bigger than the bigger that you want to subtract the smaller from. So Leibniz makes this condition explicit in a text called De ratione et proportione. There he said explicitly that the condition must hold because you only dig here with two things that are finite. So as Filippo already mentioned, this Archimedean property is captured by the requirement, by the concept of homogeneity. So it is captured by this requirement that the thing you compare, that the things that have a ratio between each other are homogeneous. So as he said also, homogeneity is basically the universal basis for fine estimation. That is, it gives us a equality between things that are not similar under every aspect, and for which a comparison from the point of view of quantity is not obvious. And from this, we can build a more exact way to compare them using antipharesis, but we really have to work from homogeneity as Filippo presented. So notice that antipharesis involves nothing beside the two line segments. So their quantitative comparison or ratio seem to arise just in virtue of the two being given with their parts. That is, you just do the subtraction and you have the ratio. Reciprocally, it seems that according to Leibniz, as soon as you have homogeneous things, well, there can be exactly compared between each other using the division procedure. For he writes, for example, those things are homogeneous, whose magnitudes can be expressed by number by assuming the same measure for all of them. In another text called De Quantitate, he writes, two homogeneous things have a common measure that can be approximated as one please. Excuse me. But so this would make for a very extended domain for the mathematician's estimation. It seems that as soon as two things share some features which make them homogeneous, then we can just apply the mathematician's estimation. And so we could apply it, for example, for speed, because two speeds can be homogeneous. We could apply it for densities, because two densities for Leibniz can be homogeneous. We could apply it for line segments, etc., many things that many attributes which are considered important in physics for Leibniz are attributes that make things homogeneous. Well, I think that we have to resist this conclusion, not only because it is not consistent with how Leibniz framed his theory of estimation according to the repetition of a measure, but also because he is explicitly aware that this doesn't work and that there are limitations to the mathematician's estimation. And so let us get to our next condition. It is the extensivity condition. So as Filippo also showed, for the mathematician's estimation, the subtraction involved in the application of antipharesis is the mereological subtraction. And in this case, the remainder and the part subtracted are disjoint. And basically, this is how you get a magnitudes. That is, from the point of view of the mathematician's estimation, a magnitude is obtained by the breaking down of a thing into parts, okay, according to the Euclid's algorithm. So basically, it is even stronger than what we call additivity. I think it is really that the thing that you measure or estimate, well, there must be things with disjoint parts. And otherwise, it's like the mathematician estimation does not see the magnitude of the thing. So here is how I frame extensivity condition. The magnitude of a thing arises from the number of its disjoint parts of different magnitudes. That is from the disjoint repetitions of the measure and of its refinements. So I think that this view on the importance of this extensivity clause becomes very plain if we look at definition of quantity that Leibniz gives when he looks at things from the point of view of mathematicians' estimation. So this is something that this is a quote that Filippo already gave, but this is in a different translation, it's mine. So here Leibniz writes about quantity. Quantity is expressed by the number of congruent and disjoint parts which comprise the thing to which it is associated. So basically, if you cannot break down the thing into disjoint parts, you just cannot express the quantity of the thing. It's how it's framed here, at least. So this puts a constraint on the kind of magnitudes one can estimate using standard methods of estimation. So basically, the kind of magnitudes that we can estimate are those that are partes extra partes, or whose quantity is extensive. So for example, we can think of line segments, we can think of mass in things also, but there are magnitudes which Leibniz explicitly says are not extensive. These are the partes intra partes magnitudes, the intensive magnitudes, such as speed or density, where by definition, this is not the case. I think that one intuitive way to make sense of this and to see why this wouldn't apply is, okay, just imagine that you have two bodies that are the same and that have the same speed, that is as one, and you kind of take the system of these two bodies together. So you have a system that has mass as 2, but its speed is still as 1. So if we say, okay, we start with this bigger system and we break it down to obtain the speed of the system, it doesn't work because we have two parts with a speed as 1. So it's as if like the procedure that Leibniz had in mind in that design stops there. It doesn't work for intensive magnitudes. But we have to say that there are hypotheses which allows to extend the procedure to intensive magnitudes. It deals with this, for example, in the Dynamica. But still, I think it's preferable to say that, okay, we have this mathematician's estimation, which is a theory that stands of its own, and we can add further hypotheses to extend it. But it's important to look at the restricted theory also. So now I want to turn over to the last condition, which is the fine estimation condition. So notice that in general, the sequence of quotients, the order quotient obtained by applying the procedure of antiphrasis or division in turn determines the ratio of a quantity A to some quantity M. That is, equivalently, given some measure M, the quantity of A is determined by the sequence of quotients. So this is made plain and stated explicitly by Leibniz in the specimen Luciferae. There he writes, thus, the magnitude is determined by the number of parts that are equal between each other, that is, the quotients, and that are unequal in agreement with a fixed rule. And it is allowed that one thing be commensurable relative to the measure or relative to things to which the measure exactly repeated is congruent, and yet by a subtraction continued to infinity, either of the thing from the measure as many times as possible, or of the measure from the thing as many times as possible, and of the residue from that which is subtracted from this process through the progression of the numbers expressing the repetition, that is, through the sequence of quotients. Leibniz writes, is known the quantity of a thing relative to the measure. And for this reason are equal those which are in the same mode regarding the same measure in relation to repetition. So what Leibniz is saying here boils down to something simple. The sequence of quotients is a criterion of identity for ratios. If two ratios have the same sequence of quotients, they're the same. If they're different, they're different. So this is displayed most clearly in what we call the continued fraction form of a ratio. When it is expressed as a fraction, for example, take the previous example I gave for Euclid's algorithm. we had 17/5. So here, if you look at the denominators of the continued fraction here that I'm pointing to, you see that they are just the order quotients that we obtained by Euclid's algorithm. Similarly, if you have a ratio that is rational, so a ratio between two commensurable quantities, the denominators here are just the quotient in the sequence of the denominators here are just the quotient in the sequence of quotients that you obtain by applying Euclid's algorithm. And you can also have infinite continued fraction, and there it's the same. The quotient will be the denominators will be the quotients that you obtain by your division in turn. So Leibniz is aware of this. Leibniz is using this notation for continued fraction, exactly this one, and he makes the link with the sequence of quotients. So for example, this is a text from Initia Rerum Mathematicarum, and it is in fact from this text that I took the example of 17/5. Leibniz writes the following: that be given two straight lines, whatever be the way they are compared to each other. For instance, we subtract the smaller from the bigger as many times as possible, and in turn, the remainder is subtracted from the smaller, and in turn, the remainder of the smaller is subtracted as many times as possible until either exhaustion follows by subtracting from the ultimate term the existing measure, if the quantities are commensurable, or a law of progression to infinity is obtained if the quantity are incommensurable. He writes after that, and the sequence of quotients will be the same as the proportion is the same. Once again, we have this criterion for identity. He writes after that, in fact, if A is to be as this continued fraction expression is to the unit, then L, M, and P will be the sequence of quotients. For instance, this is our example. If A is 17 and B is 5, the sequence will consist only of L, M, N, whose numbers will be 3, 2, 2. Now, one way to segue smoothly to the fine estimation condition is the following. So nowadays we have this fact that all positive real numbers have a unique continued fraction form. So you have here you have to be careful how you relate the finite sequence of natural numbers to the continued fraction form that I mentioned earlier. But I'll just glide over the detail and say that there is a bijection from the rational numbers, so numbers that are expressible as fraction of integers, to the finite sequences of natural numbers, and there is a bijection of irrational to infinite sequences of natural numbers. In fact, structure-wise, there is something more going on here, but I won't go into details. But I mean, if people are interested in mathematics and things like this, I could elaborate later on this. A question we can ask is, was it a fact for Leibniz that all magnitudes have a one-on-one correspondence to sequence of natural numbers or to sequence of quotients, either finite or infinite? So we can approach this question as follows. Okay, antiphyresis allows for infinite sequences of quotients. Infinite sequences of quotients arise whenever the two quantities compared are incommensurable, so the ratio are irrational. Leibniz knows this. Moreover, Leibniz knows that and say that irrational ratio are determined by their infinite sequences of quotient. We saw this earlier, so it seems here that we have some kind of injection. So to each magnitude is associated just one sequence of one infinite sequence of natural numbers. Now we can ask the question, well, does any kind of a sequence of natural number is any kind of sequence of natural number associated to a magnitude? So kind of we would have a surjection, but so it also seemed to be the case because Leibniz, for example, in such excerpts writes down that you have this continued fraction form here that results from a division as the one contained in Euclid's algorithm. And here the denominators, basically what they are, well, they seem to be kind of arbitrary natural numbers. So they're ABC, it doesn't say what. And here again, it seems that the continued fraction can be infinite. And again, we have the same thing in the Initia Rerum Mathematicarum. Here, the LM and P, they seem to be any kind of natural number that we could think of. They're quotients, so they have to be natural numbers. So is it the case that we have this one-on-one correspondence? Well, we have to be a little careful, nevertheless, even though what I say seems to be true, because for Leibniz, his aim when he comes up with estimation and fine estimation is to provide an exact scientific knowledge of magnitude. So we kind of have to have a firm grasp on those magnitude and on the sequences that determine them also. So let me make the issue more clear or more precise for you. So suppose that we're given two magnitude, each incommensurable to the same unit m. Well, how do we know that they are different or identical? Okay, well, we look at the ratio, and these ratio are associated with sequences of quotient. Now, how do we know that the sequence of quotients differ or are identical? Well, it's more complicated here. So we have to see if they correspond in order, the quotients. But how do we know that we took into account all quotients? We have infinite sequences. How do we know that? So a way to make up our mind about this is to look at a precise example where Leibniz shows how we can determine a magnitude using a sequence of quotients. This is an example drawn from a text called De Ratione et Proportione, where Leibniz addressed this issue of determining a ratio through an infinite sequences. And he shows how this is done in a particular case. The case at hand is the reciprocal of the golden ratio. Leibniz writes, when numbers are sought, it is understood that it can be exhibited either nearly, namely through approximation, if this remains somewhere within the approximated thing, or exactly by the infinite sequence, if is investigated the progression of the approximations itself. Since indeed in this way all approximations are expressed simultaneously, it is manifest that the thing itself, which is our object, is expressed exactly, since indeed in every single case, the error can be made smaller and smaller to the point where it can be shown smaller than any given quantity. In all cases, at last, it will be made null. Thus, in the line cut in extreme and mean ratio, this is the golden ratio, we will express all quotients in this way. Here we have the reciprocal again. So, sorry. So, here we have that Leibniz gives us some answer in this particular instance for the question of how we can determine a ratio by an infinite sequence which arises through antipharesis. So basically, in the present case, you have a way to know that the progression of continued fraction to the infinite sequence of ones in this case, is a better expression for the quantity sought than all finite progression of ones, which approximate as closely as one wishes that quantity. So basically, the idea is, okay, give me some error, good. Then there is some finite sequence of ones, which determines a rational number that is whose difference from the quantity that we're seeking to approximate is smaller than the error that you gave me. And I can do this for every error that you give me. So basically what I can say is, okay, let's take all the finite sequences of one. We have this infinite sequence of ones. And because it contains all the finite sequences of one, it will be, its difference to the quantity sought will be smaller than any given error possible. In fact, it will be the exact expression for the quantity we're seeking. So I want to make two observations. I'll be done in a little bit, so in 8 minutes max, concerning what I just said, two subsequent observations. So first, in general, for a quantity incommensurable to a measure to be exactly determined or estimated by an infinite sequence of quotient, there needs to be an actual infinity of quotient given. So I think that this is obvious in the way Leibniz frames things here. For example, he said that in the way that we're presenting this continued fraction, all approximation are expressed simultaneously. So this all means that it is an infinite that is greater than any number that you can think of. They are all there. Here also this idea that we will express all quotient in this way. Again, it's really, he speaks of omnes in Latin. So this is important. It's not just a fluke. It's not just something that appears only in this text. In fact, Richard Archer has translated a text towards a science of the infinite, while Leibniz presents a very elaborate conception of infinity, where he makes such claim for series and sequence in general. That infinite series of or sequences must contain an actual infinite number of things. So it cannot just be potential. It's not just, because otherwise we will just have an approximation. We'll not have an exact expression. Second, one needs to have the law of progression for the sequence to judge that the infinite sequence exactly determines the quantity. The idea here is that we need to have some firm grasp on the magnitude that we're expressing. And we need to see that, in fact, we have to go to infinity to really capture the magnitude. So it's not just in virtue of the fact that the division in turn does not terminate, that we have a precise determination of the ratio. We have to have more, and this more is the law of progression. For example, Leibniz writes in On Magnitudes and Measure, but now he's talking about the infinite sequence of quotients. He writes, but this sequence of quotients, if it is established by a fixed law that they express all the smaller can be subtracted from the preceding one so many times whatsoever, will give a scientific comparison of the two magnitudes. So I'll just skip these slides. It's not that important. So basically, if we look at des rationnés et proportionnés and at des magnitudes and Matsura I just quoted from, basically we have this expression that the law that I've been talking about. What it is? Well, it is concise, so it gives a knowledge of how a sequence provides ever closer approximation to the quantity to be estimated, so that in the end, there is no difference between the sequence and that quantity. So it gives us an idea that you really need to incorporate all the infinity of quotient and none besides. So I just want to observe that Leibniz seems to think that all infinite sequence of quotients have such a law, although we may not be aware of it. So in the Initia Rerum Mathematicarum that I quoted from earlier, you remember he said that you have two cases when you apply the division in turn. Either you have that you have a finite sequence of quotient, or you have a law. So it seems that you always have a law. So now I would surmise, and Filippo would surmise, that the law in question is a condensed, what it consists in, well, it's some condensed expression which generates the whole sequence of quotient as a sequence of approximation for the quantity sought, and the error of this sequence of quotient becomes infinitely small. So in the end, our question about the one-on-one correspondence of sequences, both finite and infinite, and magnitudes, it hinges on the nature of this law. So I can elaborate on this during the Q&A, but basically, if we have that the law must be, in Leibniz's mind, either an arithmetical formula or something that is computable, then we cannot have a one-on-one correspondence for reasons that are mathematical. So it's proven. And now we can go to the fine estimation condition. So what it is, well, a magnitude is estimated or known exactly in relation to a measure m if either the ratio am is finite. So I mean the sequence is finite, so the sequence associated to the ratio is finite, or the law for the infinite sequence of quotient associated to am is known. This law gives us a method for knowing that all the necessary and actually infinite quotients are there through approximation. And this gives us also an answer to a previous question. How do we distinguish between infinite sequences? Well, we have the law. With the law, through the law, we know which quotient must be there and their order also. So now let me just lay out the formal procedure for the mathematician's estimation very quickly. I'll be done in 2 minutes. So basically, you start with an extensive quantity A of a thing XA. And what you do, you fix a measure M that is anything homogeneous to the thing XA to be estimated. Then in virtue of their mere homogeneity, they are comparable in the sense of Archimedes. So the smaller can be subtracted from the bigger some finite number of times. After that, you apply the procedure of antipharesis or of division in turn between XA and M. And the resulting sequence of quotients gives you a criterion of identity. And it gives you the estimation of the quantity A of XA if it is finite, or so if the sequence is finite, or if the law of progression of the infinite sequence is known. So we have to remember that we have three conditions imposed on our procedure for it to give us an exact estimation of the magnitudes of things. These are the ones that I enumerated earlier. And last, notice that we surmise that there are the following interesting consequences for Leibniz scholarship, which follow from our reconstruction of estimation. First, you have that infinite number are impossible. So this would support Rabouin and Richard Archer conclusion in a forthcoming paper. And it goes against Katz and many other scholars. We also have that argument which Leibniz says are drawn from Mathesis Universalis in favor of his measure MB squared. Can in fact be backed up by the reconstruction that we gave here. And so there is and so Leibniz was Leibniz is vindicated in saying this against what Freudenthal say in an article on the controversy between Papin and Leibniz, where he says that the art of estimation that Leibniz mentioned was not elaborated on further by him during the 90s. We also have this result that we can pinpoint the question of which real numbers Leibniz could have had access to, since real numbers are his concept of numbers is based on estimation, and we have this correspondence between sequences and magnitudes. That the correspondence between magnitudes and sequences hinges on the nature of the law. So if we settle this question, we settle the question. So if we settle this issue about the law, we settle the question. And our reconstruction also advocate for the key role of actual infinity in Leibniz's conception of mathematics against, for example, Breger, who says that only potential infinity matters for Leibniz in mathematics. In fact, actual infinity for Leibniz is crucial in mathematics because in the 90s, everything hinges on quantity, and quantity hinges on estimation. So this was my talk. Thank you all. Thank you, Professor Garber. Thank you, Professor Dumitru. It was very generous to have us today.
Thank you very much. We have time for some questions. If people can use the chat function to indicate that they have, or actually not the under reactions, the raised hand, I think would be very helpful. Although I notice already there is a comment by Dennis Dogchi. Would you like to speak?
Sure. This is going to be for Filippo. I think towards the end of his presentation, he identified Leibniz's view of positive integers as being wholes of abstract units. And if I didn't misunderstand that, then here are some questions that we can ask to Leibniz about that, and whether Leibniz has anything in his writings on these subjects that would answer if Frege raised it to him. So in some of the earlier sections of the Foundations of Arithmetic, there's discussion of unity, Einheit, and the number one. So what is an abstract unit? So that's something that Frege does. How many abstract units are there? Is the number one identical to an abstract unit? If there are more than one abstract unit, then are there different number ones, different number twos for collections or wholes consisting of such units? And if we extend this account? Are these, I mean, can we extend this account to natural numbers? And in which case, what is the number 0? Concerning 0, perhaps Leibniz does say something explicit, but I was wondering questions along these lines. How would Leibniz account for or respond to such questions on Frege's part?
So, okay, well, thanks very much. So the notion of abstract unit, so the abstract unit enjoys a very specific status in Leibniz. So when I said that essentially all positive real numbers can be accounted for in terms of this estimation procedure, I meant to say all positive real numbers, but the number 1, essentially, but the abstract unit. And I mean, it's quite difficult to exactly say what the abstract unit is. I mean, generally speaking, the notion of unity is considered to be an innate notion. And it seems that the abstract unit in mathematics is a kind of abstraction from the notion of metaphysical unit. But the idea concerning like the other question is that, so for example, is there a number 1? So while the number 1 can be considered as the abstract unit, I think that's at least that seems what Leibniz is doing. And well, how many abstract units there are? The idea seems to be that you can consider, you can take any number. I mean, essentially, there are accounts of number where Leibniz says you start with the abstract unit and you add the abstract unit to itself. And the idea seems to be that I mean, there are as many abstract units as you wish. But because I think the key point is that what really interested Leibniz, for example, when he takes this repetition of a measure, is that what you are repeating is congruent. So you are repeating something that so a prime, a second, and a prime and second, they must be congruent. And so it seems that what really matters is not what you are repeating, the object that you consider and that you are repeating, but only the fact that they are congruent. And in this sense, so when you ask if there are more than one abstract unit, U1, U2, and so on, what is really important there is that you consider objects which are disjoint, if you are thinking of this merological addition, and that they are congruent. Sorry. So in a way, I think that Leibniz would regard these like Fregean questions with a bit of suspicions, in the sense that, well, what is the difference between the number 1 and the number 2? Well, essentially, the number 1 can be identified with, you can take any object and consider it as a measure, and so consider it as your unit to estimate something. And the number 2 is just the fact that you are considering 2 congruent objects. So you consider one as the unit, and then you consider another object congruent to it. And the idea is that I've got 2 congruent objects. If I consider one as my unit, then I've got essentially 2 units, and I've got the number 2. Yeah, and then with regard to the number 0, yeah, so well, I see like the message that Richard Arthur has just written. So the unit is not an absolute thing. So yeah, exactly. You can consider different things as your unit according to what you're doing. And with regard to the number 0, there are other papers where Leibniz has another approach to the notion of numbers. So he has a more algebraic approach where he tried to define like the basic properties of the basic operations that we can have about numbers. In some papers, he deals with like natural numbers. In others, you find this approach with regard to real numbers. And there you find the number 0, because essentially the 0 is the neutral element of addition. So you get that a plus 0 is equal to a, where a is a magnitude, an arbitrary magnitude. So the number 0, as I see it, is justified in terms of a different approach, a more algebraic approach of numbers, where essentially you start just by lay down the operation, you define the operation that are valid for numbers, and there you find also the number 0. Yeah, for the time being, I would say I would give you I would give this as an answer.
Okay, Dennis?
Can I quick say something, or should we just move on? Now, at one point, you did say that perhaps there is just one abstract unit. And in that case, we can't quite define the number 2 as a whole made with units plus what? That's what, there is a question. I mean, Frege does take these in some detail in these sections. And if there are infinite, if there are anything, any abstract units, one thing, then we can consider a different abstract unit here, abstract unit there. Then the number 2, well, is it the collection of these 2, or is it the collection of these 2? Are there different number 2s? So those are the questions that do arise if we take. If we take one line on what the abstract unit is and how many there are, or if we take the other way around. And these are the things that I was wondering whether Leibniz has any considerations.
Well, if you take like a collection of 2 objects, 2 abstract units, so for example, like two lines, I don't know, and then a collection with 2 squares, which are congruent with each other. Well, I guess the idea is that the number 2 is neither of the 2, but it's like the equivalence class that you get from the.
Yes,
essentially, because it's the point I was making with the notion of ratio that is more abstract than the pairs of magnitudes that have that ratio. So at least in this approach, where you start with the estimation procedure, essentially numbers should be introduced as equivalence classes. So in this sense, it sounds close to Frege. But yeah, I mean, the idea, if I said that there is only one abstract unit, I'm not sure I said that, but anyway, the notion of abstract unit is a relative notion. So when you have a plurality of objects which are congruent, you can take any of those objects as a unit and you have a plurality of unities, essentially. That's the basic ideas.
Okay, so the equivalence class idea gets us very close to Frege in that regard, but that wasn't the definition that I was gathering from Leibniz's account. So if that's so, then great.
But indeed, I mean, the claim that naturals are wholes of unities is a claim that you can justify as a specific case when you take this estimation approach, okay? But it's not Leibniz's last definition of number. Indeed, he used, I mean, this is just numbers as a multitude of unities is just the standard Euclidean definition. And Leibniz used it, I mean, the young Leibniz used it, I guess, until 1677. Then he said, well, look, I've got a new definition, a better definition, and the definition is that numbers is what is homogeneous to the abstract unit. And I didn't stress a lot this point, but thanks to the estimation procedure, not only you can vindicate both the claim, but essentially naturals as collections of units is just a special case of this more general characterization of numbers as what is homogeneous to the abstract unit. So yeah, but thanks a lot for the questions.
Thank you very much. We have a question from Sam Eklund.
Okay, hi. So my question, mainly for Filippo. So the first, just a minor, maybe nitpicky thing. I think I heard you mention that Leibniz uses in essay for the part-whole relation. And at the very least, by the time of the initio rerum, in essay is sort of that general broader concept. He doesn't use that for part-whole, so he'll say in that one that I think it's here. I pulled up the quote. I can post that to the chat. So he says that's if we posit the latter, we must also posit the former. So if we posit a finite line, positing its endpoints. So just in there, the in-essay relationship, he does use that as a generalization of the part-whole. But then he go on to say, well, a part-whole is when you have something that has the in-essay relationship plus the homogeneity condition. So just like I said, a minor kind of nitpicky point. But then I guess my second one was about the epistemic claim about positive integers not necessarily being basic entities, because we kind of derive them from these continuous things. And I guess as an epistemic point, I could see that if we're already from the starting point of having continuous quantities, but the epistemic story of how we get there can be kind of convoluted, where we take, contiguous things in the phenomenal world, and then we they have real parts, and those real parts are defined by various motions and forces. But to get to the actual continuity, then we do this abstraction procedure of, well, maybe you have something, a line in the real world, and it's divided into these various parts in certain ways. But now we imagine all the ways this line could be divided. It could be divided into thirds, into halves, into quarters, and all this stuff to get to that abstract notion of continuity. And then from there, we could use the estimation procedure to get to natural numbers from that top-down approach. But if we're doing this thing to get to continuous magnitude in the first place, well, couldn't I also then use the bottom-up approach for the things I counter in the phenomenal world? Well, some of them are already carved into discrete parts, and I don't have to take this detour of thinking about extrapolating to continuity and then going back to number from there. But I could start, say, there's 10 people in this group, and there I'm counting. I'm not, don't have to think about it in terms of continuous quantity. I can kind of just jump straight from these given things I think of as unities. Does that make sense?
Yeah, I think so. Yeah. Okay. So concerning the first point, I agree that in essay is not a part of the relation. Yeah. So if I said something that
very nitpicky point.
I didn't want to suggest this, and this is not only true for initio rerum, so for 17, 15 or 16.
Yeah, something like
that. But actually, it's already true in the 80s.
Yeah.
Already in the papers on real addition, we find that the in-essay relation is a broader relation, and when we restrict the in-essay relation beyond homogeneity, we get the part-whole relation.
Yeah. Even in the 70s, he was thinking about that in terms of the container-contained relationship. So the way that rational is contained in the concept rational animal, he says that's sort of going to be more general than.
Yeah. So on that point, I think that it should be clear now. On the second point, it's true that essentially. Well, it seems to me that like the estimation procedure requires that essentially we can divide a line. If we take the case of lines, we can divide a line essentially in infinitely many ways. Mm-hmm. It's very clear. Sometimes it says quantity is an indefinite number, or is the material basis for number. So. Mm-hmm. And which means, and when you fix a measure, you make like the potential parts in a certain magnitude. Mm-hmm. You in a way, when you fix a measure, so the idea is that you have a magnitude and you can divide it infinite in many ways. When you fix a measure, it's like you are deciding in which way to divide the magnitude. And so it seems that he's committed to the idea that you can divide a magnitude essentially wherever you want. So there must be some like completeness axioms at least working there. And if we look at the definition of continuity that he gives, one of the two properties that make up the definition, well, is that if you consider what he calls co-integrand parts, so parts that when taken together, they are equal to the whole,
Mhm.
they must have one point in common. And
Yeah.
essentially, if you suppose that there are holes in a continuous line, well, you can cut the line in a hole, and you will get two parts,
Mhm.
two subparts of the line that have nothing in common, that they don't have the point in common. So that condition in the continuity definition implies that we have something like the completeness.
Mhm.
And so it seems to me that actually we must take the magnitudes as continuous in order to apply the estimation procedure.
Mhm.
So like the continuity is another like prerequisite for the estimation procedure. And yeah, I mean, you can take also the other approach. So from discreteness to essentially to explain the continuous, and for example, when he wants to explain extension in terms of like the discreteness of the monads and so on. But at that point, you are working. I mean, it's Leibniz that makes this quite strong distinction when he says, look, when we're looking at metaphysics, the parts are prior to the wholes. So we start with discreteness and we want to explain continuity in terms of discrete objects. But when we are looking at ideal entities, so in mathematics, the mathematical notion of continuous is the other way around. So the whole is prior to the part. So I was there essentially proposing an interpretation of this claim. And the idea seems to be that, I mean, when you perception is already something abstract. There is a certain amount of abstraction that in perception. And so it seems the idea seems to be that like continuous magnitudes are in some sense given as a whole. And by breaking them down, we get to like discreteness. Yeah.
Okay. I guess one other thing I was thinking that might kind of help that claim is, so for some things we number that like maybe start out discrete, say we have 20 people in a group, then we start with, each individual, we add them up to 20. We can kind of compare them, say we take half that group, well, then we can compare that part whole because those, say 10 people were part of the original whole of 20 people. But if we have one group of 20 people and a different group of 10 people, well, now there's no part whole relationship. So it seems that procedure then making them homogeneous to the abstract unit would be allow you to compare the 10 people of one group with 20 people of another group, because even if there might not be any members in common, you kind of have this procedure of how you could relate those to homogeneous units. So I think that might be one advantage of that top-down approach then, is that even when you're talking about discrete things in the real world, you're able to tell a story of how you can compare their quantities, even though they're discrete things, that even if they don't have any parts in common, by assigning kind of each discrete individual to the abstract unit, if that makes sense.
I would just add this point. So when I started to talk by talking about the logical conception of number, that is a bottom-up approach.
Yeah.
So really you start with unity, you add unities, and so you take like a very different approach than this estimation conception of numbers. So we are not claiming that that approach is not present in Leibniz. We actually think that we have at least these two big different approaches, and we were just interested in the estimation conception of number.
Cool. Thank you.
But thanks very much. Yeah.
Great. Daria?
Thank you very much. It was a very interesting topic and very interesting discussion. I suppose I first met this idea of estimation by comparing the lines between them in Hermann Helmholtz's theory of measurement. And so I was very impressed to see the same ideas in Leibniz. And I have a couple of questions, very simple too. First, of course, this type of method of estimation is very well applied to lines, to finite lines, and I suppose also to angles. Could you indicate other types of extended entities which can be estimated by this Euclid procedure? And the second, what about time? It's clear we are starting to represent time by lines in the early modern period. But it's not very clear how can we measure periods of time by the same procedures as you described. Thank you.
You want me to answer this, Filippo?
Yeah. Please go
Yeah,
ahead.
okay. Okay, so thank you for the question. It's a super good question. Basically, one other example would be the mass in something, because it's just something that is proportional to the volume, and there is an obvious way of how we would go about like dividing or breaking up the volume into parts. So this is one example. This is one further example. I think that in some texts, Leibniz and Richard Archer could correct me on this if I'm wrong, have this idea that time is something that is extended and for which we have a notion of congruence. And so that you would have been able to apply some of these methods to time, take it as something, as soon as something is extended or as disjoint parts, it seems that the procedure as we frame it is applicable to times. And in fact, Leibniz has this theory. It's something that Dr. Oscar Esquizabal in Argentina has been working on. So in the Dynamica, he has this theory about ductus, so about products between intensive and extensive quantity. And what happens is when you use ductus, you can make up extended product out of something that is extensive and something that is intensive. So for example, if you take volume and density, so density is intensive, volume is extensive, you get mass, and mass is extensive. So he has to propose like further hypothesis to do this, but he gets to something that is extensive. And like, what you want to do, if you want to measure density from there, you just fix, you just take two things which have the same volume, but different mass, and the density will be proportional to, so they have the same volume, but they have different mass, and the density will be proportional to the ratio of the masses. So, but you see that it necessitates like further argument to make this point. It's not just out of the ease mathematician estimation that you can get the ratio.
Yeah, but I suppose it's interesting that in any case, you have to reduce magnitudes to something extensive. I mean, even in case of mass, it's not the mass itself can be measured, but the like pondus, this by the proportion of the like you call this type of I don't remember the static mechanism.
The lever.
Lever. Yeah. Thank you. But what about, I don't know, intensity of sound or the pitch of sound?
This is a big problem in Leibniz. So there are intensive magnitudes which seem to be like correlated to an extensive magnitude in a very intuitive way. So for example, density seems to be, it seems possible to associate it to an extended magnitude to get mass. But Leibniz also says in some texts that you can measure sounds, you can measure heat, you can measure light. And I think there is no obvious way of how to do this based on what he says in many different texts. So at first I thought that he always had to have ad hoc hypothesis as soon as he wanted to measure some intensive magnitudes. Now it seems that he has some kind of general method to do this for many things in physics, using what I said about products of extensive and intensive. It's the notion of ductus, but for still that, like there are many intensive magnitude that evade this treatment. And I think that, for example, what you mentioned, sound, I don't know exactly how he would have done it. It's possible that there is some text where he proposed a method for it, but it's really not obvious to me. And I mean, I think that in some case, Leibniz mentioned the medieval theory of latitudes. So with remissions and intention and everything. And so he seems to be thinking that, okay, any kind of intensive magnitudes and quality that they deal with, I can deal with too, but I don't know how he would have done it. So we're still looking for answers to this question. So yeah.
Thank you.
Rick Arthur has a comment. I think we've only got a couple of minutes.
I'll be very brief. I just wanted to say on Daria's question about time that that Leibniz does indeed think that different times can be congruent to one another. Of course, for that you need a measure, and to get to the measure you need to have something like a uniform motion. So it is more complex, but there is that bridge that he mentions. Of course, it's traditional, right, that equal times will be spelled out by equal distances with a uniform motion. But anyway, I just wanted to say that much.
On that, I was gonna let me just briefly raise the question that I was going to raise, where there is obviously no time to really talk about it. Extending both of those comments, Jeffrey, in your last slide,
Yeah.
you mentioned the question of the status of arguments from MV square.
Yeah.
For MV square, and the way in which these considerations regarding quantity and measure enter into it. And I'm really sorry not to be able to hear more about that, because that's an intriguing comment. From your last couple of comments, I can sort of see the direction in which that would go.
Yeah.
But I'm sorry that we don't have time to discuss that in more detail.
So me and Filippo actually were working on a talk for the seminar in Hanover next summer, and we will present how explicitly how this would go. But so I hope you'll be there. But I think that we can frame many. So Leibniz in text with Papin, as many of you may know, he says that the measure of Descartes, it violates this important law of estimation. And I can see that the error in many cases where people estimate through MV goes back to this error of estimation. And basically, I think that with the way that we reconstruct the estimation, we can make this claim in Leibniz rigorous and show that there is, in fact, a sense where this would have been convincing also to other people of the time. Basically, if I can go, I'll try to say it very quickly. Basically, the idea was that this theory where you determine a ratio through a sequence of quotient, it was well known at the time. And the idea also of conservation of force and of energy was supported by many different physicists at the time. So the idea would be that, okay, if you can associate two different sequence of quotients to the same quantity, then there is some kind of inconsistency in your theory, and that's what follows from Descartes' measure.
Great. Well, we all have something now to look forward to for next year.
Thank you.
Thank you very, very much.
Thank you, guys. Thank you for having us.
Thank
It was
you.
a pleasure.
Come back next week, where David Barta and Arf Ben-Yami are going to be talking about the emergence of idealism. So have a good week, and maybe we'll see you next week. Thank you very much.
Bye.